pretty happy. Okay, so use summation and limits, or a Riemann sum is what that's really trying to say to evaluate that. So if you remember, these will always have two elements that are always the exact same thing, right? It's going to have a limit, and it's going to have the sigma thing. So limit as n goes to infinity of sigma from I equals 1 to n. So those are going to be, those elements should always be there in some form or fashion. And now we try to do the specific stuff, right? So that's really easy. When we try to set things up, let's keep in mind what it is we're actually doing. What's kind of the overall concept of the thing that goes in the sigma? Base times height. It's the area of some rectangle. So of those two things, I would say that the base is usually the easier of the two things between the base and the height. So for this particular example, what would you say the general format for the base should be? 4 over n, right? Because from here to here is a length of 4, and we are trying to squeeze an unspecified number of rectangles into that interval. And so we're going to call that n, and so each rectangle would be 4, the total width, divided by the number of rectangles. Okay, so base length will be 4 over n, so there's base. And then the height, of course, is going to depend on where you are at on the picture. More specifically, the height is going to be determined by, in this case, what? What is going to tell the height how high to be?
The equation inside the integral.
Yeah, the y value.
Right.
The y value for that function, right? The 5x. That's exactly right. So what I'm going to say is 5 input, 5x, right? Now this is not going to just be some random x. It's going to start and stop at some pretty specific places, and it's going to work its way across in a pretty consistent pattern. So what was the very first thing you put inside the input parentheses? -3, right? Because that is going to be the lowest conceivable x value on the interval. Is that right? 1, 2, 3. That makes sense? Okay. So then we need to progress from left to right, and so we need to add a little bit, and then add a little bit more, and then add a little bit more, so on and so forth. So every time we add a little bit to get to the next rectangle, how much will we add? Yeah, the width of each rectangle. Yeah, so it'd be plus 4 over n, and then we have to multiply by that summation element because, there we go, we need to multiply by the summation element because we need to actually progress from 1 to 2 to 3 to 4 to 5 to 6 as we work our way across the picture. Okay, obviously we could do some rearranging and some simplifying, but in its most basic form, that would be a good setup. You guys agree? We good? So the looks on your faces are, we're a little tired. That wasn't that hard, so let's move on. Did I read you all correctly? If I read you wrong, you can tell me. I'm reading the tired thing right, I know that. But about the we get it, so move on thing, am I right? Okay, cool. All right, so you could continue on. This would be a great exercise for you, by the way, because obviously you all can evaluate that integral like that, right? Wouldn't take you very long at all. You could even use a calculator if you felt really lazy. But then if you wanted to check to see if you can actually evaluate one of those Riemann sums, you know that you'd be working towards what you know to be a correct answer. So feel free. You could use those formulas to do that if you choose. All right, let's move on. We're going to do a little bit more work here in 4.3, maybe get started in 4.4 a little bit. Yes. Okay, so we're going to talk about the word area here and negative and positive values of integrals. So we just saw this in the previous example. Some of the function could fall below the x-axis. In this case, the definite integral will show up as a negative value. This is simply because we are accumulating negative numbers, right, that we're adding up. But we would never say that the area is negative. So if I ever tell you the area of such and such is blah, 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 I'll always give you a positive number, right? I'll say the area is 10. The area is 5. But if that area falls below the x-axis, realize that the integral will interpret that as a summation of negatives, and so it would actually spit out a negative number. Does that make sense? Even though we look at it and we're like, well, you told me the area was 10. Yes, I told you the area was 10, but the integral is going to see it as a negative 10 because that area fell below the x-axis. So with that in mind, if we look at the integral from -4 to -1 if we actually integrated and we told the definite integral, hey, we want you to add all this stuff up. What do you think the calculator would give us for that particular definite integral from -4 to -1? It would give us -6. And of course, if I said, all right, this little purple area that I'm highlighting, if I said, what's the area of that? And you said -6, I think we'd have to disagree, wouldn't we? Because you really can't have a negative area. If I said, hey, the area is 6, and then you noticed that it was below the x-axis and you did the integral, you'd have to give a negative answer, wouldn't you? Because the area is below the x-axis. Okay. What if we did the integral from -4 to 2, kind of stretching all the way across, starting where we did before, all the way over to there? 0, right? Because as I accumulate the first part, as we found a second ago, we're going to get -6. We're just going to continue to accumulate. You would see that the next triangle is the exact same size and even shape, but it's just above the x-axis, and so the integral will interpret that as adding up a bunch of positives, so it'd be -6 plus +6, and that would give us 0. Now, does that mean the area is 0? Of course not. A nice parallel with this is the concept of displacement versus total distance traveled, right? So you woke up in your bed this morning. Hopefully tonight, later on, you'll go to sleep in your bed. And so for your day, your displacement was 0. That doesn't necessarily mean that you stayed in bed all day, though, does it? In this case, you're obviously here, so you didn't. And so while for the day, your displacement would be 0, your total distance traveled would be something more than that, because you actually got here and did your thing, and then you went back home. So your total distance traveled would be like 10 or 20 miles or whatever. And this is a nice illustration of that, of kind of a displacement versus distance traveled concept. Does that make sense? Unless you decide to sleep here. Are you going to sleep here tonight? No? Okay, me neither. I could not. I couldn't do that to my wife. Who knows what my son will do tonight? We'll see. Okay, any questions at all? Okay, cool. All right, well, let's move on. All right, so some properties here. Yes, perfect. We're doing good. Looks like we're not going to get that there. Nope. Okay, so some properties here we need to run through. The first one, integral from -a to a, not -a to a, excuse me, the integral from a to a should always be what? 0, yes, because if the two limits of integration match, there's no way to squeeze any area in there. So we just say 0. An example, of course, if you ever saw the integral from 4 to 4 of f of x dx, hopefully you would in less than 2 seconds be like, oh, answer 0. And believe it or not, that will actually happen from time to time. You'll actually get, it won't just like directly ask you that question, but in the process of maybe doing something else, you'll get something like that. And I'd want you to recognize it and just see instantly, hey, that's an easy one, 0. All right, integral from a to b of f of x is equal to the opposite of the integral from b to a of f of x. So if you switch the limits, you're supposed to switch the sign. Once we get into section 2.4, not 2.4, 4.4, we'll look a little bit closely like why that is. But for now, if we can just remember, if you switch the limits, you got to switch the sign. That'll be good enough. Of course, if we saw the integral from 5 to 2 of f of x, to me, I don't know how it is with you guys, to me, my comfort zone is to always accumulate from left to right, because I always read from left to right. I just probably a habit. I probably should try to break that habit. But if I see an integral like this, the integral from 5 to 2, that's accumulating the other direction, and I always am a little uncomfortable with that. So this would be a case where I personally would probably switch the limits. And I'd say, well, you know what, I would rather it be the integral from 2 to 5, because that's, for me, is more of a conventional direction to accumulate those little rectangular areas. And so in order to do that, I have to change the sign of the whole integral. So that'd be a time when maybe you would use that. Okay, let's see here. Then number 4. This is basically to say that a whole thing is made of 2 parts added together. The integral from a to c could be rewritten as the integral from a to b plus the integral from b to c. if you think about this in terms of area, hopefully this makes a lot of sense. If I take the area from A to B and the integral from B to C, if I take those two areas and add them up like we are on the right-hand side there, then I should get the entire area from A to C. Good? Okay. So then how would you guys rewrite the little example there, the integral from 1 to 3 of f of x plus the integral from 3 to 7 of f of x? Any thoughts on how we'd rewrite that? Yep, integral from 1 to 7 of f of x. That's exactly right. So again, you can probably see how this could come in handy as far as both directions, really. Like we will do this in both ways. We will take one integral and split it up into two parts potentially, or we'll take two integrals and combine them down into one part. I think depending on the situation, either way could be useful. Okay, and then the last two here, integral from a to b of k f of x, k standing for a constant. Do you remember, what can you do with the constant?
Take it out.
You can just get it out. Yeah, so that can be particularly handy as well. In a lot of situations, we'll practice that a lot this year. So just getting that constant multiple out of the integral can make the integral look simpler. You might be able to see a pattern easier than you would have with it in there. So an example here, integral from -5 to 8 of 7 f of x dx. You just bring the 7 out. 7 times the integral from -5 to 8 of f of x dx. Okay, and then the last one, I think, is one that it's easy to just gloss over, but this one might be the most useful one for you this year. And I'll give a little foreshadowing. You guys all will know what I'm talking about for the most part. But let's look at it here kind of in its most basic form. The integral of a sum or difference is equal to the sum or difference of some integrals. So I could take this first one and I could split it up and say, well, really what I'd like to do is the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And so if I've got a sum of integrals, then what I can do is simply split it up if I've got the integral of a sum, I can split it up to be the sum of integrals. And I can go the other way too. I could smash them back together if I wanted to. An example right here. And this is actually going to be a pretty nice example of why this is useful. And I'll show you another one as well. So we could say integral from 3 to 4 of x to the 5th dx plus the integral from 3 to 4 of 5 sine x dx. So I've split it up by using a sum concept here. But what is one other simplification or manipulation I could do here? And get the 5 out. Yeah, the constant multiple. So if I do that, integral from 3 to 4 of x to the 5th dx plus 5 integral from 3 to 4 of sine of x dx. Now this is about as simple as it gets, and as long as we can do our antiderivatives, we'd be in pretty good shape. So let me point out why this would be handy in this specific example, and it really is the 5. So somebody perhaps, and I'll make a stronger case for this in a second, somebody could perhaps do this. What if, I'll do this in blue. What if somebody did this? They said, hey, look, there's a constant multiple. There's a 5. I want to get that thing out of there. What if they did this? Would you have any problem at all with that? Why? Yeah. The 5 was not a multiple on the x to the 5th. See how somebody could do that? Okay, so that's a sort of a strong case. To me, here's a stronger case. In section 4.5 later on, we will look at examples like this. What if we had the integral from 2 to 3 of x plus cosine of 3x? So I don't know how everybody learned this last year, but I know that I taught my folks the Timmy thing, right? And so the Timmy thing, if you've never heard of that, we'll talk about that later, but it's basically, Timmy is the worst. He is. He always messes up. The second part of the integrand, like Timmy's messed up, hasn't he? Isn't he missing a factor of 3? Because the derivative of the inside of cosine of 3x is 3, and that would need to be part of that integrand, right? to make this work. And so somebody could easily do this. They could be like, oh, we're missing a factor of 3. And so they would go in there and they'd say like, well, let's fix that. You're welcome, Timmy. And they'd do this. Feel real good about it, except that's wrong, isn't it? Because once again, the x is kind of an innocent bystander in all of this. And all of a sudden, the x has gotten multiplied by 1/3. How's that okay? It's not. And so what you would do here, what you do here, hopefully, instead of that, is you would recognize, well, I could split this up, integral from 2 to 3 of x. You can't see that. So let's try this. You could say integral from 2 to 3 of x plus the integral from 2 to 3 of cosine of 3x. Here we go for number 1. We're doing the definite integral from 1 to 2 of x squared minus 3. So we're going to, for our first step, find the antiderivative. The antiderivative would be 1/3 x cubed minus 3x. And then the notation, we want to put that in parentheses, evaluated from 1 to 2. That tall vertical line means that evaluated from x equals 1 to x equals 2. And that's actually a fair point. Later on, when you get to a Calc 3 setting, putting x equals 1 to x equals 2 will make a big difference because there could be all kinds of stuff going on there. So that's what we are doing. No need at this point probably to do that. And then we evaluate. So let's see here. If I plug in the 2, I'm going to get 8/3 minus 6 minus 1/3 minus 3. And as we talked about a little bit, I think, in a free response setting, especially on the AP test, don't you just stop right there? If it's free response, you have to stop right there, because anything you do beyond that is potential for mistake, for which there is no reward anyways. So you might as well stop right there. If it is multiple choice, you do have to keep going, so I am going to do that at least. So let's see here. -6 plus 3 is -3, and 8/3 minus 1/3 is 7/3. Does that make sense? And then getting a common denominator and adding, I think we'd end up with -9/3 plus 7/3. So I got -2/3. Anybody take it that far? We good? Okay. Let me ask you a question real quick. Why didn't we put a plus c when we did the antiderivative right here? True, but we did do an antiderivative, didn't we? So shouldn't there be a plus c in there? What's the antiderivative of x squared minus 3? It's 1/3 x cubed minus 3x. Who's to say it couldn't be plus 12? Wouldn't that still fit the antiderivative pattern? I'm getting at a minor point. Why wouldn't it matter? Aren't you about to subtract it anyways? And more importantly, wouldn't the c in the first evaluation be the exact same thing as the c in the second evaluation? And so c minus c will always be 0. So my point is, I suppose, that there is a c there. We just don't write it because 100% of the time it'll just be subtracted out to 0. For whatever that's worth. So I guess I'd like for you to understand why we don't write the c there, and other times we do write the c. The definite integral just subtracts it out. So I don't know if we're just being lazy or efficient, call it whatever you want, but we're just not going to put it there because it's going to subtract out every single time. Okay, so number 2, what manipulations did you guys do? Anybody want to volunteer to number 2 before you actually started to work on the antiderivative stuff? Did anybody get the 3 out? So you could, Blake obviously suggested the rational exponent. That's good. The 3 can come out. A couple of options there, right? So I think the rational exponent you got to do for this to make sense. This just becomes a power rule for integrals. So it becomes 3 times 2/3 x to the 3/2 evaluated from 1 to 4. And at this point, you probably could see, of course, that the 3's cancel out. And so you're just left with 2x to the 3/2. So here, the rational exponent thing comes into play. It'd be 2 parentheses 4 to the 3/2 minus 2 parentheses 1 to the 3/2. And 4 to the 3 halves is 8 times 2, of course, is 16, minus 2 times 1. Did you get 14? All right, fantastic. Any questions? All right, number 3, we move into our friendly trig neighborhood. Yes, the antiderivative of secant squared is tangent. There's, of course, ways to prove that without just remembering it, but in my opinion, it's just easiest to remember it. So we end up with tangent of x evaluated from 0 to pi over 4. We try to execute FTC1 by evaluating at pi over 4 and evaluating at 0 and subtracting. So Alyssa asked a really good question. She said in a free response, is that right there, is that considered to just be arithmetic? And the answer is yes. So a free response setting on an AP test or whatever, you most certainly could leave it just like that and you should get full credit. Of course, you might use the answer later, or it could be a multiple choice. We do want to be good at simplifying, so let's talk about it. Tangent of pi over 4 from the unit circle is 1, and tangent of 0 is, and of course you could leave it like that if you wanted to, or you went this far, how about just 1? All right, and then finally with number 4, let me move this a little bit. Number 4 has maybe the most manipulation. What do you do first here? Got to deal with the denominator, right? Because at this point we really don't like fractional integrands. So we need to flip it up. What does that do to the denominator? Makes the exponent negative, right? Yeah, the exponent has to be negative, and I was talking with those folks over there. That's the number one thing that I see people forgetting. So when you flip up, 2x plus 1 still is in the numerator, but it becomes x to the negative 1/2 when you flip that denominator up. So just be careful. It's not like you don't know what you're doing, because you actually do. Just be careful and don't mess that up. At this point, even with the dx in there, we still kind of have an issue, because we'll talk about later how an integrand that is a product is really just as much of a pain as an integrand that's a fraction. So what should I do? What can I do? Yeah, you can distribute, and so you should. You really should. So this will take it out of being a product. So it ends up being the integral from 0 to 9 of 2x to the 1/2 plus x to the negative 1/2 dx. And this might be a time when you want to split it up into 2 different integrals if you want. I don't think that that's necessary. I think we just leave the 2 in there and kind of handle it as we go. But that would be your choice. That would certainly be an option. So let's see here. It'd be 2/3 times 2x to the 3/2, so 4/3 x to the 3/2 plus 2x to the 1/2, all of it evaluated from 0 to 9. So how about 4/3 times 9 to the 3/2 plus 2 times the square root of 9. And here's where something beautiful kind of comes into play. Do you see how both terms have an x for a factor? And the next plug-in is 0. The lower limit is 0. Couldn't we confidently say that? You want to be really careful, though, whenever you have exponentials involved, because something to the 0 is not 0. And you want to be really careful when you have trig involved, because cosine or sine or tangent or whatever of 0 is not always 0, right? And so you want to be really careful. But if you have like just powers, like polynomial-ish like things, then I think you can say 0 to the 2, 0 to the 1/2, whatever it is always going to be 0. Okay, so 9 to the 3/2 is 27 over 3 is, times 4 is 36. And then, of course, square root of 9 is 3 times 2 is 6. So I got 30. Once again, recognizing that in a free response scenario, oh, is it plus 6? Yeah. Oh my gosh. So, unintended, but classic case of a loss of point for absolutely no good reason. The thing I was about to bring out is certainly that right there in yellow would have gotten you full credit if you had done what I did, which I take the AP test every year, the free responses at least afterwards, and I hardly ever get 54 out of 54. It's always some little stupid thing like that where I get a point off, or 2 points off, or something so dumb. I'm rushing through, I'm not being as careful, but even if I was, I'd probably still miss at least 1 point. Case in point, stop where you should. I love it when I give you a good example and didn't even mean to. Okay, that's it. There is